Hello everyone and welcome to Learn LEED Chapter 5. I'm Trey Hauk and today we'll be talking about energy and atmosphere. Now, a lot of the environment talk has been about global warming and emissions and the climate's heating up, but it gets thrown around a lot, but we never really understand why or how that's happening, at least from a lay perspective. Um, and so this kind of goes more into the emissions side of things, which is one of the largest LEED categories, LEED impact categories, as we discussed earlier. As an overview, we're going to first go over low energy building strategies, internal load reduction, active mechanical systems, electrical power systems, energy optimization strategies, renewable energy systems, and then last but not least, refrigerants and HVAC. So starting off, low energy building strategies, high performance buildings. So there's a couple of strategies here, and there's a bit of a bullet point list that you can kind of look through. But the core essence of it is that we are looking to use data models to optimize the energy usage of the building so that we are making the most of what we got and not going over and beyond. Now, one of these simulations are daylight simulators. This kind of examines the heating and cooling systems, the wall and roof choices, insulation, lighting, windows and doors, exterior and interior shading, and skylights in order to determine just how they contribute or detract from the building's energy efficiency. It's more valuable to use modeling in order to find how effective a change in the building's envelope and energy system is, rather than for anything meant to determine the building's actual performance. And here you have an example from a textbook by Charles Kibbert that kind of talks a little bit more about this, and some of it, like the energy usage and the savings based off of the model. So how do we verify energy performance? Well, through the organization of the International Performance Measurement and Verification Protocol. They provide an overview of the best practices for verifying energy efficiency, water efficiency, renewable energy performance, and energy conservation measures are covered in their own protocol within this. We have fuel saving measures, water efficiency measures, load shifting, and then energy reduction, which is essentially just through equipment retrofits and then modifications of operating procedures. So the summary, passive design is relying on the heating, cooling, lighting, and ventilation systems, relying on natural elements. That's your sunlight, your wind, your vegetation, anything that naturally occurs on site. When we design with passive design in mind, we want Mother Nature to do the work for us. Now, with this, there's two major design aspects. There's the reduction of the building's energy profile through the use of its location and site, and then there's the building design itself, the orientation, so that it is getting heated effectively by the sun when it rises and sets in both the summer and the winter, as that changes pretty drastically. We're talking the natural wind flow. If the wind is flowing against or with the building and naturally cooling it or counting against its insulation. You see, a good passive design is one that allows a building to default to nature. It is one that lies in a closed system, never using more than it takes. And these are just a couple examples here. I'll pause the lecture here just so you can kind of read them. But these are just a couple examples from Charles Kibbert that kind of details things that you can look at when you're designing passively. So, internal load reduction. There are what we call plug loads, which is any device plugged into an electrical outlet that increases cooling loads due to heat emissions while consuming substantial amounts of energy. Office equipment itself contributes to about 18% of a commercial building's total electrical load in the United States. And among things, we got, your printers, scanners, copiers. The number one factor that you might expect is Computers. Desktop computers are the #1 contributor to these plug loads. So how do we mitigate this? Well, we can upsize the electrical wiring. Increasing the wiring sizes beyond those required by code has the benefit of reducing energy losses in the wiring system and proportionately reducing the impact of these heat losses on the building's cooling system. From there, though, we have active mechanical systems. Starting off, we have chillers, which consume approximately 23% of total building energy, and they contribute to a high peak load during the day as they're keeping everyone cool and ensuring that building is keeping everyone alive and healthy. When we see building-related fatalities, we see failed chillers and other kind of HVAC devices coming down to it. So we really want to try to optimize them. There's 4 main types. There's centrifugal, which is over 300 tons. There's screw, which is 50 to 400, scroll, which is under 50, and then reciprocating. And each of these have their own various levels of initial cost and efficiency. But the main thing you need to know for all of them is that combining the direct digital control and variable frequency drive in an improved design can bring efficiency up to 50% better. The 2 main ones that we really want to look at when we're looking at the cooling to power ratio are our screw or scroll water cooling chiller systems. The characteristics of a high efficiency chiller plant are going to be an efficient design concept, efficient components, and then last but not least, proper installation usage, because a renewable resource is no good if you're going to use it in a way that significantly decreases the efficiency of it. It makes it less efficient than a less environmentally friendly way. Next up, we have air distribution systems. That would be the A of our HVAC, which includes air handlers, electric motors, ductwork, air diffusers. The list goes on and on. Anything that circulates air through the building is an air distribution system. And the ways we can kind of optimize that are through variable air volume systems, low pressure ductwork design, that is oversizing the ductwork, and then decreasing the velocity of our air handlers and properly sizing the VFD motors just so that we are reducing the amount of stress and the power that is needed for those air distribution systems to effectively function. From there, we have energy recovery systems, which come in 2 main categories. We have economizers, which bring in outside air in appropriate conditions, and then we have energy recovery ventilators, which are placed between the exhausts and intakes, and is kind of just meant to be a way to help circulate the air in a more efficient system rather than just direct pumping in, pumping out. From there, we have the 2 approaches for ventilation, air, and carbon dioxide sensors. You can either bring that constant outside air in or just use sensors to activate systems when the CO2 levels are exceeding over a permissible level. From there, you have water heaters. The 2 main solutions we have for that are tankless water heaters and solar water heating systems. Both are renewable ways. They're still experimental technologies, but they have proven to be more efficient in the long run over your stereotypical water heater. From there, we have electrical power systems. So starting off, fluorescent lighting. Fluorescent lamps range in efficiency from 80 to 93 lumens per watt, while the max efficiency of 200 lumens per watt is achieved by LED lights. So with the increase in technology, we're seeing so much more optimized energy usage of our LED lights. We still want to make sure that when we're specifying the lighting system that the lamp and ballast are electrically matched and the lamp and fixture are optically matched, which is a lot of jargon for essentially making sure that we want to make sure that they match so that we're getting the most efficiency that we can out of them. From there, we also want lighting controls. There's 2 basic functions of an ideal integrated system. Lights on/off depending on occupancy, and then lights dimmed or brightened or on/off depending on daylight. there's a little excerpt of a textbook here from Charles Kibbert. But the long and short of it is, dimming systems pay themselves off in the long run, as while there's an initial upfront cost, if we look at that life cycle costing, we'll see that it saves much more money and energy through the energy bill. From there, we have electric motors. We want to look at the variable speed and electronically commutated motors. They typically consume about 4 to 10 times their purchase cost in electricity, but the more efficient motors use more copper or aluminum and less steel, as well as finer, smaller ball bearings. So from there, we have to talk about innovative energy optimization strategies. First off, there's radiant cooling. You have a concrete core, metal panels and cooling grids, and even sometimes a water wall feature. This is essentially a more passive form of cooling the building rather than an active chiller. From there, we have ground coupling, where we have ground source heat pumps. If you have it be horizontal, more shallow, it's going to be cheaper and it's going to take you less skilled labor. But if you do vertical, it's more common, it uses less land, but it's also going to be more skill intensive and more expensive. You can kind of see an example here of some of that ground coupling. This one in particular is used for fresh air and chilled water. And then from there, we have renewable energy systems. So this is what you might expect. We got your solar panels, solar energy, or otherwise known as photovoltaic panels. They are semiconductor devices that convert sunlight into energy. And there's a growing number of these building integrated photovoltaics, as we refer to out there, some of which are virtually transparent or partially shading, which can even be used as sunshades and skylights. It's an industry that's rapidly growing, but it isn't the most efficient yet. In addition, we also have wind energy. That's going to be your wind farms. This one is one of the fastest growing forms of energy production, with an estimated 25% year-on-year growth. And not only that, but we've also seen a dramatic cost reduction from about 40 cents per kilowatt hour in the 1980s down to less than 3 cents per kilowatt hours today. That's more than, I want to say, 1,000% decrease. Now, the Eiffel Tower uses wind turbines, funnily enough, to power many tourist areas within, amounting to about 10,000 kilowatts per year. Not all wind energy has to be these giant, massive turbines. Sometimes they're smaller devices that are just integrated with the building that we don't see, but continue to actively power and facilitate our energy needs. This one might surprise you, but another renewable energy source is actually bioenergy. By creating energy using agricultural and wood waste and animal and municipal wastes, we're shifting the money spent on oil that could be taken and impacted to rural areas, and also creating a whole new industry of using things that we already utilize in our modern day society, but oftentimes just get thrown away because we don't have a use for them. As David Morris puts it, we move away from a hydrocarbon economy to a carbohydrate economy. Good old biomass energy. Here is a table that kind of talks about the advantages and disadvantages of both, because at the end of the day, you're going to want to choose a solution that fits best depending on the particular solution that you've devised. From there, we have fuel cells. The process of energy generation is well described as the reverse of electrolysis. Bit of a hard word to say there, because during electrolysis, water molecules are split into hydrogen and oxygen, while in fuel cells they're smashed back together into water, generating electricity. Types of common fuel cells we have phosphoric acid, alkaline batteries, molten carbonate, solid oxide, and then a proton exchange membrane. While it is expensive to use reformers on non-hydrogen cells to extract this hydrogen, it's becoming more and more viable as fuel cells designed specifically with buildings in mind are starting to hit the market. So, Now we get into it's one of the more common topics of LEED and of environmental sustainability, and that is the ozone depleting chemicals in HVAC and CNR. So in the past, we used CFC 11 and CFC 12, and otherwise known as chlorofluorocarbons. It stopped in 1986 because it was having a ozone depleting effect, and we realized that if it kept on, we weren't going to have a planet to live on. So we took immediate action, and now we use HCF-134A. It's non-ozone depleting, it's smaller, there's no need to remove the refrigerant, and there's rumors of a propane-based refrigerant being developed, but for now, HC-134A is the well-known and accepted refrigerant used. So kind of wrapping things off here, I want to ask, what is the core strategy of reducing emissions through all of this? Think on that, and I'll see you next time on Learn LEED.